After studying this module, you will be able to understand number 1, the basics of nuclear collective model, number 2, knowledge of collective vibrational model, number 3, knowledge of collective rotational model. Nuclear reactions, direct reactions. Now, in this particular slide, we want to look into the direct reactions in a more deeper way. So now in this slide, basically the focus is on the kinematics of neutron stripping DP reaction. So first of all, the stripping reaction is there, that is stripping reaction form of direct reaction is there. So what is happening is this red nucleus is the projectile nucleus which is hitting the purple target, and then after the nuclear reaction, again the red nucleus is moving along this theta direction, and the blue one, product nucleus, is moving along the other direction. So now here we can see that this is the diagram, and in the diagram the momenta are given. The momenta of the incoming particle, momenta of the outgoing particles are given, theta angle is given, and then if we plot a triangle, if we plot these three vectors, then we can find that they form basically a triangle, and then Pn square is equal to Pd square plus Pp square minus 2 PdPp cos theta. Nuclear reactions, direct reactions. So now in this slide we will continue our discussion about direct reactions, and in this slide we are going to study the mathematical formulation which are used in case of direct reactions. From the law of cosines and reaction kinematics, Pn square is equal to Pd square plus Pp square minus 2 PdPp cos theta. From conservation of angular momentum and fact that reaction occurs at the surface, L square is equal to L bracket L plus 1 h bar square is equal to R square Pn square, where R is the radius of the interaction. Above equations show a relationship between angular momentum I transferred in the reaction and angle of emission theta of the product. And what is that relation? That relation is L into L plus 1 h bar upon R square is equal to Pd square plus Pp square minus 2 PdPp cos theta. Nuclear reactions, direct reactions. In this slide we are going to see that how the differential cross section of direct reactions varies as a function of scattering angle for different values of angular momentum involved and the energy. Now here in this slide basically a picture is shown in which we have the plot of differential cross section in arbitrary unit as a function of scattering angle for different angular momentum and q value. In this case we observe that the differential cross section varies as a function of a scattering angle for different orbital angular momentum and q value. In the lowermost curve, which is for L is equal to 0 and q is equal to 2.5 MeV, we observe that the scattering cross section decreases sharply from its value at theta is equal to 0 degree, and soon it reaches to 0 for angle around scattering angle around 35 degree or so. But for increasing value of L, for example, the second curve, the differential cross section initially increases up to 10 degree or so, but after that it shows a reduction. Then again at around 30 degree or so, the reaction cross section increases a bit, but then decreases. The third curve from the bottom also indicates more or less the similar behavior, whereas the fourth curve from the bottom, which is there for L is equal to 3, Q is equal to 3.2 MeV, the behavior is that the differential cross section initially increases up to theta is equal to around 30 degree, but after then it reduces. So we conclude that for the given L value, the differential cross section basically has different behavior with increasing Q value. Nuclear reactions, compound reaction. So in this particular slide, we are going to study what are compound reactions and what are their characteristics. We know that in the compound nuclear reactions, so far what we have learned is that two nuclei undergo reaction. They basically come so close together and they are there for such a long time that they form a composite system. And then that composite system basically form a unique entity, and then some energy and momentum distribution happens among the nucleons, and then it starts decay. So what are the characteristics basically? The first important characteristics we observe is reaction involve many interaction and collisions, and that lead to complete thermal equilibrium inside compound nucleus. So as I said, the two nuclei are basically interact with each other. They are for such a long time so that they completely mix. When they mix, then the energy of the system, energy of the incoming nucleus basically, or the energy of the total reaction is basically distributed among the nucleons, and the thermal equilibrium inside the compound nucleus is established. Second important characteristic is, since energy equilibrium require time, the compound nuclear reaction are sufficiently or significantly slower than direct reactions. So this is another important characteristic. Since number of steps involved are large, so only statistical methods are adopted, because nucleons inside the nucleus are basically very small, so quantum mechanics is applied. So when quantum mechanics is applied and the energy distribution among the nucleons take place and the thermal equilibrium is achieved, then in order to study that process, only statistical method. We cannot apply the classical methods for such a small quantum system. So we need to apply the statistical methods in order to see what is happening inside the nuclei. The compound system releases energy by emission of neutron, protons, particles and gamma rays, but has a lifetime of the order of 10 to the power minus 19 seconds. So once the thermal equilibrium is achieved among the nucleons inside the compound nucleus, then depending upon how much energy is there in the compound nucleus, it starts decaying either by particle emission or by gamma ray emission. But its lifetime is of the order of lifetime of the compound nucleus before decay. That is when the compound nucleus is formed and when it starts decay. So the time difference between these two is of the order of 10 to the power minus 19 seconds. Nuclear reactions, compound reaction. In this slide, we are going to study the compound nuclear reactions and the conditions required for compound nuclear reactions. Now compound nuclear reaction basically are based on an independent hypothesis. What is that independent hypothesis? The idea of compound nucleus formation was given by Neil Bohr, who postulated equilibrium of energy. So Neil Bohr basically gave the idea of compound nuclear reactions, and according to him, when the two nuclei, that is the projectile and the target, undergo nuclear reaction, then they get combined together so that they form compound nucleus, and when they form compound nucleus, then the energy distribution among the nucleon takes place. The entire energy of the system is basically taken by the nucleon and distributed among themselves. So after some time, there is an equilibrium of energy which happens in the compound system. A direct consequence of equilibrium, energy equilibrium, is that the decay of compound nucleus does not depend on the way it was formed. So as per Neil Bohr, when the equilibrium of energy takes place in the compound nucleus, then it forgets its previous history. Previous history means it doesn't remember how it was formed. So it's a direct consequences of equilibrium of energy. With large number of collisions between nucleons in the compound nucleus, the information on entrance channel is fully lost from the system. As we have seen that in case of compound nucleus, the projectile and the target remain in contact with them for a longer period of time, so that large number of nucleon interaction happens between them, and in that process the information on entrance channel is fully lost from the system. Consequently, the decay of compound nucleus depends only on the mass and atomic number, excitation energy and angular momentum. So it means after the formation of compound nucleus, when it starts decaying, then the output of the decay or the decay process is primarily guided by the mass, atomic number, excitation energy and angular momentum of the compound nucleus. Nuclear reaction, compound reaction. In this slide, we are going to study the compound nuclear reaction graphically or pictorially. Here in this slide, basically it is shown that how the compound nucleus are formed. So in the picture you can see that a small nucleus is getting in contact with a bigger nucleus. Then in the reaction, after the reaction, the composite entity of the two nucleons is basically formed, and with the passage of time, the two nucleons within the composite entity basically get involved. The nucleons share the energy of the total system, and in this way an equilibrium state is developed. Once it is developed, then the compound nucleus has the energy, equilibrated energy, angular momentum and the mass. And now once it starts decaying, then the decay basically depends upon the value of these parameters. Nuclear reactions, compound reaction. In this slide, we are going to study the thermal energy equilibrium happening in the compound nucleus reaction. As we have understood from the discussion in the previous slides, that the key hypothesis of compound nucleus formation is that thermal equilibrium happens among the nucleons in the compound system. Thermal equilibrium means particles emitted from compound nucleus have Maxwell-Boltzmann distribution like vapor molecules from a liquid. So it is well known that if a system is under thermal equilibrium, then the things coming out of that system will have the Maxwell-Boltzmann distribution. In the same way, since in the nuclear reaction the compound nucleus is formed where the thermal equilibrium happens, or you can say that the energy redistribution among the nucleons happen, so there is a thermal equilibrium, and therefore the particles emitted from the compound nucleus will have Maxwell-Boltzmann distribution. The Maxwell-Boltzmann distribution describes a probability of a particle in ideal gas to move with a speed v. The properly normalized distribution is phi v dv is equal to bracket m upon 2 pi kt bracket 3 by 2 exponential minus mv square over 2 kt bracket close 4 pi nu square d nu, with 0 to infinite phi v dv is equal to 1. Nuclear reactions, compound reactions. So in this slide also we continue our discussion about the compound nuclear reaction. To fit to measured Maxwell-Boltzmann distribution of particles provide information on the temperature and density of states in the compound system. So Maxwell-Boltzmann distribution of particle basically is the nature of nucleons inside the nucleus. So distribution, temperature and density distribution of the nucleons inside the compound system basically follows the Maxwell-Boltzmann distribution. So we can say that if we fit the density and temperature distribution using the which is the Maxwell-Boltzmann distribution, then we can get information about the temperature and density of states. Another important thing is that Boltzmann distribution is valid for a large number of systems, especially at large temperature. It is invalid if quantum properties of the system start to dominate, which usually happen at low temperatures. Nuclear reactions, compound reaction. In this slide, basically few graphs have been shown. These graphs are basically representing the distribution of probability density as a function of speed. The shape of these graphs is the Maxwell-Boltzmann distribution type, and these graphs have been plotted for various noble gases. Now here we can see that depending upon what gas we have a different kind of Maxwell-Boltzmann distribution for them, and it is observed that heavier is the gas, more sharper is the Maxwell-Boltzmann distribution. Nuclear reactions, compound reaction. In this slide, we are going to study the cross section, that how it is calculated in case of compound nuclear reaction. Now cross section, we have understood that cross section gives you the probability of happening of a nuclear reaction. So it's based upon independent hypothesis, that is A plus A, capital A plus small a will make C, and then C decays into capital B plus B. So the reaction cross section for this kind of nuclear reaction depends upon capital A, that is the mass of the projectile, mass of the target, then small a, that is mass of the projectile, B mass of the product nucleus, B mass of the light charged particle emitted, and EA is basically the energy involved. So sigma is equal to, for this reaction, sigma is equal to sigma C into PC, where sigma C is the cross section for formation of compound nucleus C with excitation energy EC and angular momentum LC by entrance channel A plus A. P, probability for the decay of compound nucleus, what is PC? PC is nothing but probability for the decay of compound nucleus C at the excitation energy EC and angular momentum LC into the exit channel. So the above equation simply means that the reaction cross section in compound nucleus reactions is basically the product of reaction cross section for the formation and the probability of decay of compound nucleus at excitation energy EC and angular momentum LC into the exit channel B plus B. Nuclear reactions, compound reactions. In this slide, basically the time scale of happening of compound nuclear reactions is shown. The collision time depends on the velocity of the projectile and the size of the target. So collision time when the compound nucleus is formed by the projectile and the target, the collision time or the interaction time depends on the velocity of the projectile and the size of the target. How it depends? Because the time is calculated from the range in which the reaction happens divided by the relative velocity or relative speed between the projectile and the target. So collision time depends on the velocity of the projectile and the size of the target. So here in the picture it is given that the collision at the collision state, which is called the entrance channel, tau is of the order of from 10 to the power minus 21 to 10 to the power minus 23 second, or collision probability. But when then the compound nucleus is formed within this time frame, then mass energy distribution is equilibrated. After that, once the things settle down, then the decay of the compound nucleus happens, and decay stage of the compound nucleus is called exit channel. This decay happens in the time range of 10 to the power minus 15 to 10 to the power minus 21 second, and for that exit channel we have the cross section as sigma AB, that is probability of forming particle B. Decay time depends on the type of particles emitted and the excitation energy of compound nucleus. Nuclear reactions, compound reactions. Now in this slide, the plot of reaction cross section as a function of beam energy is shown for the decay output of compound nucleus reaction. These plots have been generated by using the particle evaporation code like PACE for the reaction 100 molybdenum. When 100 molybdenum is bombarded by 16 oxygen, then the release of 4 neutron makes 112 tin at a reaction of 72 MeV. So here in this case basically various reaction cross sections are given. So in the decay of compound nucleus, as it is clear from the picture here that 4 different nuclei are produced, 110, 111 tin, 112 tin, 113 tin, and which shows that at different energies these cross sections are different. So students, let us summarize what we have learned in this particular module. We have seen that very many concepts have been discussed in this module, but now it's time for us to recap or to summarize what we have learned out of those concepts. Number 1, neutron stripping cross section depends upon Q value of the reaction. The second thing what we have learned in this module is that compound reactions are slow compared to direct reactions as they involve many nucleon-nucleon interactions. Third important thing that we have learned is that in compound nuclear reactions, the exit channel does not depend upon the entrance channel. Fourth important thing that we have learned in this module is that in compound nuclear reactions, as the thermal energy equilibrium takes place, the particles emitted follow Maxwell distribution.